So a lot of these slides actually are by Marco Chiesa. So thanks a lot to him also for sharing some of the inputs here, also some of the results I'm going to present. Communication networks. Now we're talking about realistic communication networks. I want to give a little bit of background in the beginning, what's going on in this area. So it's become a critical infrastructure. I think we know a lot of data center applications are using data centers today for health, business, entertainment, etc. And especially the network to data centers, inside data centers, and from data centers are currently very dependable infrastructure of the society. Actually, the requirements that these networks have are quite stringent, of course, and nevertheless, we often have this news, right, that there are disconnections, disruptions. Some of these examples here actually also affected the telephone service, emergency service 911 recently, and a lot of these outages are due to configuration errors. And actually, because of the complexity of the networks, a lot of these errors are also due to human errors. So these networks are complex, and then misconfigurations happen, and then actually could have been prevented if you had the software that takes care of these configurations. Even tech-savvy companies, they struggle to get their networks right. So I just put some examples here. There was bridge loops in GitHub. There were mirroring storms in Amazon. There was corrupted router data in GoDaddy, and there were also interruptions at United Airlines. Okay, maybe United Airlines is not one of the most tech-savvy companies, but a lot of these interruptions, again, are due to configuration errors. There's no big surprise here because networks are complex. Today, a network of something like 500 routers, which is a moderate size, has configurations of the orders of millions of configuration lines. So it's really complex configurations, and a lot of these configurations have to be done manually. And of course, that's complex. And the problem is also that the tools we have today to manage those networks are really old tools. They're like from the 90s mostly. You know, probably TCP dump, traceroute, and these are relatively simple tools. And one nice example I tried to give, by the way, if I share the screen, do you see Said's video also? Then maybe I move it down here a little bit. One nice example from Beckett and his colleagues is the following one that maybe also as a motivation for this complexity here is a data center. And this data center consisted of two clusters, one on the left, which is having public services that should be reachable from the outside, and the cluster on the right that is a private cluster. And actually everything was set up properly in this data center. So they put rules here at the edge of the data center to announce everything that comes from here, from this globally reachable cluster from G, and X and Y, they block the traffic that comes from here, from the private part of the data center, from the private cluster. So that's all good. So what can go wrong in such a scenario? Well, what happened here is that there was a link failure. So the connection here from G to X, there was a link failure. So that led the traffic to be rerouted via Y. So the traffic from G was rerouted to Y. And then from Y, it was routed to C. And now traffic was coming from C to X. And of course, it was not blocked because now it was coming from the global or reachable cluster over there. So that basically leaked to the internet. So the message here is configurations are complex, but if you even have to think about failures, what happens under failures, then of course it becomes very hard for humans to reason about. So a lot of the efforts recently in this area went into automation, like software to automatically check misconfigurations, also perform what-if analysis, like what happens if a link is down? Will policy still be fulfilled, or can there be violations of the network policy? Just to give you one more example here, there's been this example that actually Barefoot Networks provided. There was a Wall Street bank that had outage in their data center, and that cost a lot. It was something like $1 million per minute of lost revenue. And of course, they really quickly tried to fix or find out what is the problem there. And they basically had 3 teams. So one was the compute team, one was the storage team, and one was the networking team. And quite quickly, the compute team, they came with reams of logs. They've written some experiments to reproduce and try to isolate the error. The storage team was also very quick. They had some system logs that they found which were affected. They came with some workaround programs. But the networking team was actually lagging quite behind, because all they had were these relatively old tools that I mentioned, for example, traceroute, ping, that can test end-to-end connectivity. But for example, they cannot give you insights in, is there a congestion? What happens on the switch? So if you remember, there's a difference between routers and switches, and these tools are mainly used for, can be used to find out problems with routers, but much less with switches. So that, of course, you can imagine who got blamed in the end when you don't have much evidence to show that the problem is not in your team, basically. Okay, so that was kind of a high-level motivation. So first, I want to give you a little bit of background how resilient networking is done currently and in the recent past. And then I want to show you some of the models. And you may wonder now, what this has to do with distributed computing. So I find this quite an interesting local problem that has some connections to local algorithms, but also has some new features. So I hope I can reveal that. And then I'm also talking about algorithms to account for congestion, and in the end come a bit back to this initial motivation with configuration checking, automatic configuration checking. If you have any questions or so, just interrupt me anytime. So I think it's better to do that directly. A little bit of background. So traditionally, as you may know, networks were running distributed algorithms. So especially if you have something like a failure, then you had these routers that try collaboratively to figure out a new path, or for example, a new shortest path. So in networking, one distinguishes between control plane and data plane. And in the control plane, traditionally distributed algorithms were running. For example, for link reversal or computing shortest paths in a distributed manner, and so on. In the data plane, that's basically the functionality of an individual device. For example, forwarding. So these routers here, they communicate together to solve, for example, shortest path problem, and then they push a forwarding table to the switch or router then that is doing the functionality in the individual device. For example, if you have a link failure, then the distributed algorithms were used to recompute shortest paths, and that's called reconvergence. So the time it takes to reestablish shortest paths, exchanging messages, that's kind of a convergence process, a distributed convergence process. More recently, software-defined networks have received quite attention, which kind of consolidate and outsource the control over the devices to a software controller. So now this become more centralized, or at least logically centralized, that you have a software running there. And for example, if there's a link failure, then a router will notify the controller, and the controller can centrally, as a graph representation of the network, can centrally recompute shortest path or also something else, and then push forwarding tables to the devices again. So the trend here was basically towards more centralized architectures. And that has different advantages. I will not go into full details. If you're interested, we can discuss it a bit later, but that recently received quite a bit of attention. One advantage of doing, or one advantage at least I can mention of centralized architectures is that you can often react faster and also in a more controlled way. So one of the reasons for Google, for example, to adopt software-defined networking like control planes was exactly also for tolerating failures or handling failures more quickly. Because, for example, you can imagine if once the controller learns about the link failure, you can recompute locally, push the rules, and there is no need to do like distributed computations so much. It has other benefits like opening interfaces and so on, but that's not so relevant now. Nevertheless, going through the control plane is still taking time. So even if you save the reconversions time, sending this information to the controller and then getting the tables back is still often too slow, especially for time-critical applications that really need a fast reaction, like gaming and so on. Good. So maybe so restoration in general in the control plane, whether it's centralized or distributed, takes time. And while you are establishing the new paths, routers may be overloaded, packets may be lost or going the wrong way. So this is something you want to avoid in critical applications. So what we use in the lecture, just to highlight this difference between the control plane and data plane, because a lot of the presentation now, or most of the rest of the presentation, will be about algorithms for the data plane, which is more local. So in the courses, we usually explain the difference between the control plane and data plane by the control plane is more, you can imagine, like the Minister of Education that manages the education for the whole country, whereas the data plane is really about like single classroom, single device, and doing basically the implementing the policies that the Minister of Education gave, and then doing it locally. I don't know whether you know our Minister of Education here in Austria. I guess Kirill and Yannick, you know this him. So there are these two approaches: control plane, data plane. Control plane can be distributed or centralized. And one example of an algorithm they are dealing with failures is link reversal. So there is a famous paper by Eli Gaffney that showed that you can tolerate a lot of failures with this link reversal algorithm, so that you can have very robust and still relatively efficient algorithms, distributed algorithms there, where you make sure that you reconnect the nodes after failures. In a data plane, the scenario is quite different. So here you need to pre-compute the tables. So it's a static forwarding table, and you need to pre-install these rules before you even know the failures. Okay, so that's the main challenge if you do this in the data plane. The trade-off here is control plane, you can do it more informed, you have global information, but then it's slow. And in the data plane, you only have local information, but then you can do it faster. Just to give you one example, so let's say we have this network here. If you want to, so FRR now will stand for fast reroute. So that's the technical term for resilient routing, basically in the data plane. So how the problem basically looks like is that you are given a network graph, and then you need to pre-install rules, conditional rules that tell you where should the traffic go by default, and what happens if there is a failure, what should the router do. So in the first phase, you define for each node or each vertex in the graph, you define a rule. If X, I will tell you in a second what X could be, then forward the traffic to Y. For example, X means if there come a packet with a destination T, then forward it to port 1. Or if a packet arrives with a source A and the destination B, and a neighboring link is failed, for example, this link is failed, then do forward this traffic here. So these rules, they can depend only on local information. So they depend on the packet, the incident links, but they cannot depend on a failure up here because the router does not locally see a failure up there. So then later, the network is operating, then maybe this link here fails. And initially, maybe the traffic was supposed to go there, but now the link is down. So ideally, you pre-computed a conditional rule that tells the router here that if this link is down and traffic should go to the node up there, then it should be forwarded to that link and then rerouted through this path. So there need to be a rule like this here pre-installed. And then, of course, you also have to make sure the path is already available. So you also need a rule here that tells the router what to do if traffic of this kind comes here, and then what traffic of this kind come here, how to forward it further. So at this stage, at the second phase of this algorithm, there is no coordination possible. That's why it's so fast, but that's also why it's so challenging. Do you see Said's picture? I just to never know whether I should move this away here. Okay,
no,
so
very good.
Okay, super, thank you. So let's look at an example a bit in more detail. So let's say we have this network here. Initially, the default route is to go from source to destination this way. And now you have these rules pre-installed. And then if this link here failed, then again, hopefully had a rule here that tells the switch that, okay, if this link, the local link is down, which you can sense locally, then forward to this link. And again, I hope that the path has been installed there. But let's say now also a link failed there. Okay, so now the traffic is being forwarded to here, but now the link is down. So this path is also not available. And there is no way that the source node can know about this, because again, in the second phase, you only have local information available. So you cannot condition those rules on remote failures. So now what needs to happen is that there's, of course, also conditional failover rules on the other nodes. So in this case, hopefully this node here will realize this link is down. So the rule could be send it back to S. And then ideally S again has a rule pre-installed that tells, okay, if the traffic is coming from this node, then and this link is also down, then forward the traffic to this on this link. So in order to realize even this simple example here, you may note that if this rule here at the source does not depend on where the traffic is coming from. So we will call this the import. Okay, so if the traffic is coming back to S and S cannot distinguish whether the traffic was coming back or whether it started here, we already may have a loop, right? Because now the S may just send it here again because it didn't realize, and then it's going back and forth. However, routers today, they provide this import matching, which means that if the traffic comes from this side, now the node S knows that, okay, I should try something else. I know this local failure, I know the incoming port is that. So then if you do it cleverly, if you pre-install your rules cleverly, then the traffic will be forward this link, and then in this case, it will work. It will actually finally reach the target. Is the model roughly clear so far? The FRR model?
Yes.
Okay, super, thank you. Otherwise, just let me know and interrupt me. So with global knowledge, all this would have been much simpler. We would have just sent directly the traffic here without. So in this example now, in the future, all the packets will make this detour, right? They will first go here, then go back. The tables are all static, so there is no learning then or improving in the data plane. So all the traffic will make this detour. It would have been much better if the traffic is sent directly on that way, if you had global knowledge. But sometimes it's hard to achieve these optimal routes directly in a distributed manner. Okay, so the main challenge is that the forwarding tables only rely on local information, and the local information can be of different kinds, and that introduces different type of models. So what kind of information could we have here? So first, or maybe as a background, so usually these forwarding tables here at the routers, they are, you can think of it as a match action table. A match action table means a packet comes, and then you match the header of the packet and maybe some additional information like the import of the packet. And then you apply an action. So you have the rules of, these are regular expressions, for example, defined over the header fields. And then you make an action that tells, in our case, it's only forward to port X. So there are only forwarding actions. And in our case, the match part, we will distinguish between different models. So one information is available at the switch is the packet header. But also sometimes we assume that we also know the, as I mentioned before, the import. So is the packet coming on this import or on that import or on the two over there? So that's also something you can match often. And then it also allows you to match on which links have failed locally, but again, only locally. And now, given that context, of course, you may ask, given the ability to install these rules ahead of time, can we tolerate one failure no matter where it happens, or can we even tolerate two failures? We already see the challenge of two failures in the example before, or maybe we can even tolerate many failures. So how many failures can we tolerate? And for answering that, or before answering that, we need to discuss some of the possible or interesting metrics that you want to consider here. But maybe before going into the metrics, one more remark on traditional ways of doing resilient routing. There is this, this is a standard that is used and is still used today in most of the networks. It's called the LFA. It stands for loop-free alternatives. Okay, so traditional networks, not software-defined networks, so traditional networks, they're based on shortest paths. So routing is always based on shortest paths. And that already, again, introduces some challenges if you want to tolerate more than a single link failure, or sometimes even if you want to tolerate a single link failure. And I want to show you an example here. So let's see this very simple network here that is a ring. And here is the source, and then there's the destination T. And this traditional network, it's based on shortest paths. Now, let's say this source wants to send the traffic along the shortest path, so it will go that way. But now this link here between S and V is down. So what S could do then is, of course, send the packet instead to U and not to V. So at U, however, again, there's no local failure information or something like that. So from U, it just will travel the shortest path. In this case, this works because now you go to U, and from there you have a shortest path that is 2 hops to T. So once the packet reaches U, it goes along the shortest path, everything will be fine. So I can perfectly protect this link here, this failed link. But if you have a slightly different scenario here, so if S is here and the destination T is there, and now this link fails, so it would be a direct link from S to T, then of course the only option that S has is push the packet to V, so send the packet to V instead of T. But now the problem is that from V, the shortest path back, or the shortest path to T, is not actually going that way as you would wish to go, but no, the shortest path is still here because the shortest path is 2 hops here and 3 hops there. So the packet will go back to S. And now you have created a micro loop. So V, without seeing any other local failures and without being able to know that there's this failure over there, you cannot protect this link. So even a single link failure is basically challenging to handle in this shortest path based fast failover. Okay, so that's in the literature that's called protection ratio. And one question is, protection ratio means how many failures individual failures can you tolerate if you set up the failover tables locally as good as you can. And there are examples that show it has been studied quite a bit in the literature. It's not a very hard theoretical problem, but you can show that it's oftentimes not possible to have this 100% protection ratio. Maybe in the end, I will come back to this example a little bit and show you one recent opportunity to actually solve this problem. Okay, so for most of the rest of the talk, I want to consider a slightly more general model that is not based on shortest paths. And I call it simply local fast rerouting problem. So let's look at the simple network again, at the simple graph here. And the basic question is, if you need to pre-install the rules in this graph, how many failures can you tolerate in the best case? Okay, and anyone has an idea how many failures or how you could pre-install the rules in this graph to make sure reachability is preserved as much as possible? It's good you think a little bit about it, but probably it's a bit early to already see some of the principles here. So I will show you this one of the basic ideas of such an example. First, of course, you can notice that if you have a lot of failures, like if you have all these failures here, then there is not much you can do because the entire network will be disconnected. So there's no way I can pre-install local rules for routing from here to there if the network is partitioned into the green part and the red part. So that's hopeless case, of course. And we will use in the rest of the talk the normal definition of connectivity. So say a network is has connectivity K. If K is basically the minimum number of links that you need to fail so that the network is partitioned. So in this example, the connectivity will be 4. So 4 link failures are enough to partition the network, right? So the two most basic criteria you may want to have in this local fast rerouting problem. One is called ideal resilience and the other one is known as perfect resilience. So the difference is a bit subtle. Let's start with ideal resilience. So ideal resilience means that you are given a K-connected graph and you want to tolerate K-1 link failures. And perfect resilience means that for any source S, you always want to be able to reach its destination T or any of its destinations T, as long as the underlying network is physically connected. So perfect resilience is slightly stronger requirement or makes less assumptions on the network. It just says, as long as the graph is connected, I also want to be able to find the route in this local way. And ideal resilience, we assume the graph initially is K connected, and we want to remove K-1 links from that graph. So of course, it's also still connected. And that's a slightly weaker requirement. So if you have perfect resilience, if you can always achieve perfect resilience, you will always achieve also ideal resilience with that algorithm. Okay, is the distinction clear of the two notions? Are they clear? We'll anyway look into examples in a second. Are there any questions on these definitions? We will see a bit later that ideal resilience, we don't understand it very well yet. Perfect resilience, it's sometimes impossible. Okay, so there's really a price you pay of being local, basically, or having to define local failover rules only on incident link information and not on remote link failure information. So that's it can be shown that that this is not possible to achieve in general. Okay, so let's start with to talk a little bit about ideal resilience. Even here, there is a spectrum of models, and more or less all of these models are realistic. Different routers support different features. And we look at to show a bit the impact of some of these models on what is possible and not. We will distinguish some of the examples here. So we will, for example, see that the resilience that you can achieve depends on whether you can match only the destination, so you only know the destination of the packet, whether you can also know the source, or whether you can also match the import. We will also talk quite quickly about what happens if you can do probabilistic forwarding. And then if you can, for example, change the packet header, which often you cannot in practice, or then you can, of course, be more resilient if you can, for example, encode information in the header about links that the packet has seen that failed in the past or something like that. So let's start with the most simple model where let's say we have we can just match the destination. And the question is, we cannot match the source, we cannot match the import, we cannot do packet rewriting, we don't have probabilistic mechanisms. So how many failures can we tolerate in this scenario? And it turns out that with this setup, you cannot even tolerate a single link failure. So the resilience is basically 0. And the example is as follows. So it is an example. So if you have a packet that starts at the source, and then the source sends it here, and now the link to T is failed. Of course, the source did not know that. Then the packet will go back to the source, and this is similar again to this example we had before. Now the source only can look at the destination again, so it will deterministically send or apply again the same mechanism and send it to here, and so you already have a loop in this case. So what is happening in a model where, let's say, you can also match the source and you can also match the import? And can we achieve, for example, k-1 resiliency in a k-connected graph here? So that would be ideal resilience, but matching both the source and the import. So maybe that's a good moment to quickly ask you. Does anyone have an idea how to set up the tables to tolerate k-1 link failures in case of we can also match the source and the import?
About the import, maybe you want to do something like if it comes from some port, then you want to send it to some port that is higher or something like this, like I don't know, to be sure that at some point, if it comes back, then you send it to a port that you've not tried already or something like this.
Very good. Yeah, exactly. That's the basic idea. You make a ordering on the ports, and then you can basically try one after the other. So now the question is only, how do you make this? How could this look like in detail? So since you know that the graph is k-connected, you know that you have k disjoint paths, right, from the source to the destination. So what you can do is basically just as you described, you try going along the first path, then until you hit a link failure there, and then you can send the packet will revert, so it goes in the other direction back. And once the source sees the packet again, and of course it will not remember the specific packet, but it can match the import, so it knows the packet from which I am the source is coming on this link. So now I can just try maybe the next disjoint path. Then maybe here it's also not working, come back, and then I try the next until I find a path that works. And if the graph is k-connected, so I can break at most k-1 paths there. So I can just try them one after the other. Here it's critical that I can match the import, because otherwise I will not see what to do next. And it's also important that I can match the source. Otherwise, maybe a packet comes back to me, but it's from a different source. So then I should not, for example, send it on this other disjoint path, but I will let it go to the original source. So one of the intriguing problems that is only partially understood today is the following. However, it's the same as before, but now we don't have the source. So what can you do if you only have the destination and you have the incoming port, but you're not allowed to use the source? And often, if we speak about ideal resilience, we mainly mean this model, because that's the in general most challenging scenario as far. Okay, so nevertheless, for some of the graphs and some of the realistic graphs, actually, we know how to achieve ideal resilience. So a lot of the high performance computing networks or data center networks, they are highly regular. And in not in all regular networks, but in many regular networks, we know how to achieve ideal resilience. And a simple example is a torus. So here I show a two-dimensional torus, but the same will work for any dimensional torus, where you have like basically a grid, and then you have wraparound edges in both dimensions. I'm not sure if someone has an idea how to achieve ideal resilience in this scenario. Maybe you can think about it for 10 seconds, and then I will show you how it could be done here. Okay, so one clever idea that, and this was by Chiesa and his colleagues that introduced this, is the following. So there is a well-known result that, or a classic result, let's say, that you can always decompose a torus into Hamilton cycles, into multiple Hamilton cycles. So in this case, we have this, so in our case 4, and so if we want to ideal resilience, we want to tolerate 3 link failures, right? So then the graph is still connected. And this decomposition into Hamilton cycles works as follows. So in this case, there will be 2 edge disjoint Hamilton cycles that you can basically cover this graph. So this should be the first one. So I didn't indicate the wraparound edges here, but the first Hamilton cycle is this orange one, and that covers all the nodes. And then the second Hamilton cycle is this blue one that then basically covers the remaining links. So now we have 2 disjoints spanning Hamilton cycles of this 2-dimensional network. So that's the first step. And then you can basically use the edges in both directions. So in all of the discussion now, the model is like this, that we can use the edges in both directions. However, the links fail in a undirected manner. So link failures are can be undirected. And so basically, the idea is that on each of the Hamilton cycles, you can always reach the destination in both directions, right? Because it's a Hamilton cycle, you can, on the orange one, you can reach the destination in this direction, but you can also reach the destination in that direction, because that's the property of the Hamilton cycle. And the same on the blue one, you can also go on the blue Hamilton cycle and then go in both directions, and always will reach the destination. So in this case, oops, forget what I said about the undirected failure. So if you want to achieve in this network free resilient routing to destination, what you can do is you first go along the first Hamilton cycle, you just travel along as long as you can. And then if you hit a failure along this path, then you reverse the direction. And again, in the reverse direction, you may reach the destination because it's a Hamilton cycle, unless there is another link failure. And then if you hit another link failure, then And now I'm talking about the directed failure. So you switch to the second Hamilton cycle, because each node also has a second Hamilton cycle incident to it. And then you follow that, and if there's a failure, you can again revert the direction, and from then on it's not allowed to have more failures, because we only want to make this robust to 3 failures. So you cannot tolerate 4 failures in this setting. So however, if there are just 3 failures, you will always be able to reach the destination in this scenario, right? Because you basically can revert and go to the other Hamilton cycle on these occasions properly, and always reach destination along that path. Is that idea clear? Okay, so that's a nice idea to realize ideal resilience. However, this only works if you have Hamilton cycle decompositions like that. So if the k-connected graph has k arc disjoint Hamilton cycles, that's what Kies and colleagues showed, then you can always achieve k-1 resilient routing. But unfortunately, not all k-connected graphs can be decomposed like that. So that raises the question, how can you do local rerouting in more general k-connected graphs? And the generalization, or the nice technique that we have today, and more or less it's the only technique that we have today algorithmically that is deterministic, at least, is the following. So instead of using Hamilton cycles, we consider directed trees. So we call directed trees arborescences. So, and instead of covering the network or spanning the network with arc disjoint Hamilton cycles, now we will span it with these arborescences. So we construct arc disjoint spanning arborescences that are always rooted at the destination to which you want to send. Okay, so for example, here's destination in this example, and this graph is for connected. You can verify that that graph is for connected. Then all the arborescence. So we have a red arborescence here, and then we have orange one and the green one. They are all spanning the entire network, and they are leading to the destinations. They are rooted at the destination D. And then the basic idea is that, or what is we are really leveraging here is that the result by Edmonds is a classic result again from 72, that you can always, if you are given a k-connected graph, you can always decompose it into this k arc disjoint spanning arborescences. So that's the analogon, or the generalization of the Hamilton cycle. So then a basic idea how to achieve resilient routing in this context is the following. So first you start routing towards the root of one of the arborescences. As long as you don't see a failure, you can continue. Once you hit the encounter failure, then you change to a next arborescence. And again, this will be rooted in destination, so you can travel along that one. And again, we have import matching. So an import, and that's one of the properties we exploit of this decomposition. The import gives you basically, or indicates to you on which arborescence you're currently traveling, right? So then you always know what is the current one. So if you have a failure, you could in principle think of just going to the next arborescence in case it's not possible here. And then the idea is that as long as if there are only k-1 failures, at least one arborescence should be intact. This sounds appealing, but unfortunately it doesn't quite work. It works to some extent, but it doesn't provide you the ideal resilience yet that we want to have. And currently we don't quite know how to get it completely. So one challenge here is that if you go to another arborescence, we want to make sure you're not going to the one that we already seen before, because then we may end up in a loop if we go to an arborescence we've traveled before. So we need to kind of have a global order enforced in which we try these arborescences. As some background, again on these spanning arborescences, so that the classic result by Edmonds, if you have a graph like this, then a first arborescence, the red arborescence, could be looking like that. So that again is spanning all the nodes. Then you can have a second arborescence that look like this. Again, this is rooted at T. And you can have a green arborescence that is again spanning. You can verify we're basically going for all the links and or touching all the nodes. And finally, the orange one that again is rooted at T. And the construction by Edmonds ensures that these are arc disjoint. So all of these arborescences, as you can see here, are arborescences. So mostly have a link in one direction and the other, but sometimes, for example, here you may also just have a link in one direction. But they're never two in the same direction. So that's one decomposition, how it could look like for this network. So the general idea would be that, okay, if you have a packet routed to T, then just go along any of the arborescences. And if you encounter a failure, then just take another arborescence. And the key question here will be, which other arborescence should you choose now on this occasion? So how to choose the next? There are two basic approaches that seem appealing. First one that is quite powerful is circular arborescence routing. So here the idea is to compute an order on the arborescences, make a strict order, and then whenever you hit a link that is failed, then go to the next arborescence according to this circular order. So again, an example, and actually this you can see when you think about this approach, that at least you cannot have like ideal resilience, but at least you can tolerate k half -1 link failures. Okay, so because the link failures now, they are undirected, so they fail in both directions, and this can affect two arborescences. So if this link fail, then both this red arborescence and also the green arborescence may be affected by this link failure. And here we have this order on the arborescence, can be any cyclic order. So what would happen now, we would start with the arborescence red, the red arborescence, and try to go along this path to the destination. But unfortunately here we get stuck because this link failed, right? So then according to our algorithm, circular arborescence routing, we would reroute to the blue. So that's the next in our order. And we try to go to the destination there, but now, unfortunately, also this link here is down. So now we would have to go according to our order to the green one. And that will work fine. But unfortunately now the link also there is down. So now we would just try the last one, but unfortunately here we are also stuck. But as long as the number of failures is less than k divided by 2, we'll always end up with the arborescence which take us to the destination, because the link failure can only destroy 2 of these arborescences. So at least something is provided by this approach here. Of course, here the network would still be connected, and nevertheless, we're not able to locally route to the destination. A second alternative algorithm that you may think could be intuitive to do is called bouncing arborescence. So bouncing arborescence algorithm is quite a simple algorithm. We try to route along arborescence again. And then if we hit a failed link, we basically bounce back on the arborescence that shares that link. Okay, so I try to go along that link, and I know because of the decomposition by Edmonds, we know we can also go in the opposite direction. And that will be a different arborescence, and we just try to go along that arborescence to the destination. The resilience of this algorithm is also not very high, but it's at least you can tolerate one link failure. And I again will show you an example here. So we start, let's say, with the red arborescence. The source is here. And now, if there's no failure, of course, everything will be fine. Now, if this link here fails, then both these arborescences will be affected. But what the bouncing algorithm does is now bounce back on the orange arborescence, because the rule is go on the arborescence which is also affected by this link. And that in this case, that will be fine, because from the orange you will then for sure reach the destination, or the yellow, let's say. But now if you would do the bouncing algorithm, and here you would like hit another failure, then the rule would be again bounce on the red, because the link is shared with the red. And now you see that the different decompositions in arborescences will lead to different behaviors here, because now we are unfortunate because we have 2 times the same 2 arborescences sharing a link. So now already in this case, we will basically try to go back by red, and we end up in a loop here. So that's it was good for 1 failure, but for 2 failures, we already have a problem, unless we try to optimize the arborescence decomposition. That's the 2 algorithms that so far people were considering. One has k divided by 2 minus 1 robustness. The other one only has, like in the worst case, is only 1 resilient. That's more or less where we stand. So one maybe appealing idea that one can think of somehow to combine this ordered routing and also the bouncing. And for example, one may try to define something like a well-bouncing arc. That is an arc that that when you bounce on it, you get basically the destination without hitting any other failure. So this definition depends on the failures. And for example, here 3-1 is not well bouncing, because if 3-1 is down, then you go on the yellow, right? But then there's another link failure there, so you're already in a loop. So that's not a well bouncing arc. However, for example, 1-3 would be well bouncing, because now if you're on the yellow, you fail, this link is failed, then you will bounce back on the red, and that will take you in this case to the destination. So that's well bouncing. And basically you could define a good arborescence is that the one that in this arborescence every failed arc would be well bouncing. And actually you can show that there is always a good arborescence. So in this case, red will not be a good arborescence, again, because of the same reason we had before. But for example, blue would be a good arborescence, because then if you bounce on it, you can take it to the destination. Interestingly, such a good arborescence always exists. You can prove that. So one could think, for example, okay, maybe I can route on arborescence X until I hit the failed link, and then I bounce if it's a good arborescence, and otherwise, if it's not a good arborescence, I just do circular routing. But that does not quite work, because then what is good depends on the failure sets, and this is not something you can see locally. So we don't know what arborescence is good. So that's not yet working, but that's at least one idea here. So that's more or less as far as I wanted to go with ideal resilience. So that's about these k-connected graphs that allow this decomposition. So that's an attractive algorithmic tool there. But so far we know how to do it k divided by 2 failures. Any questions so far? Otherwise, let's talk a bit about perfect resilience. That's more stringent requirement. So we really want to reach the destination wherever this is physically connected. And here we know that that's not always possible to achieve. And at least when we match the import and the destination. And just to give you some intuition why this is not possible, in general, let's look at an example again. So we need some definitions here first. So we need to define relevant neighbors. So we say that a relevant neighbor is one that is potentially required for a node to reach the destination. So let's look at this node I. So this is a definition with respect to a node. So we look at the routing table of a node I, and then again, we can match the import and the incident failures. And we say a neighbor is relevant if for this node, it may be needed to go via this node to reach the destination in the worst case. So for example, if there's no failures in this example here, then for node I, there's no incident link failures. There are no local link failures to I. So for this node, V2 and V3 are relevant because, for example, it could be that V2 is needed because this link that I doesn't see over there is broken. So V2 is certainly relevant. Also, V3 is relevant if that link would be failed. But for example, V1 is not relevant because if it doesn't work via V2 or V3, then it will also not work via V1 in that case. However, if you have additional failures, so let's say there is an incident link that from I to V2 that failed, then all of a sudden V1 may become relevant because now the connection via V1 may be the only one that reaches the destination. Because you cannot reach V2 directly, and remotely there may also be a link failure that prevents you from going via V3. So additional failures may make additional nodes relevant to I to reach destination. So high level idea here is that from a local viewpoint of the node I, a relevant neighbor is just one that you need to try. Otherwise, you may miss an opportunity to reach destination, and you cannot be perfectly resilient if you miss such an opportunity. So how to achieve perfect resilience? So one necessary condition to achieve it is that you need to try all relevant neighbors. So what we just discussed. So if the link to V2 is broken, then you need to try V1 and V3. And if a packet is coming from V3 to I, then eventually at some point you also need to try V1. And if a packet is coming from V1, then eventually you also need to try V3. So if there is, otherwise you may miss on an opportunity. Some basic observations is that additional failures, as we've seen, may add relevant neighbors to nodes. If you have a node of degree 2 after the failures, then if you have 2 ports, P and P prime, then eventually you have to, if something is coming in on port P, you need to try P prime. Otherwise, again, you may be disconnected on the routing level, although the graph is connected. And also, if all your neighbors are relevant, then you need to make a permutation, or basically the forwarding function need to be a permutation over your neighbors that you try. Or if only a subset of neighbors is relevant, you need to make a permutation over these neighbors to make sure that you try all possibilities that may exist. And now I want to show you an example why this is not possible in general, and actually it's not possible even on planar graphs to achieve perfect resilience. And the example the idea will be as follows. We have a graph like this, and we make sure that we will consider a node 1, and we make sure that all of its neighbors will be relevant, even without failures already. And we'll also, in our example, make sure that node 1 does not have any incident link failure, so it will not locally it will not see any failure. So that will simplify the proof. And then we also know that we must fix such a permutation for the node I that in which it tries the neighbors. And for any of these possible permutations that it can use, it will not be able to reach T under a specific failure scenario. That is still connected, of course. So in the figures, we will indicate failed links now dashed, not crossed out. And in the blue, we will indicate that in the different scenarios that may be configured, there will always be a loop. So either it will end up in this loop, or it will end up in this blue loop, or in that blue loop over there. And in any of these scenarios that we will construct, for example, here on the left, there will still be a path from 1 to T, but unfortunately the packet will end up in this blue loop up here, or here there will be a path from 1 to 3 to T, but we will, because we are local, we will end up in this loop, or we end up in that loop over there. So let's just go through all the possibilities. I'll only present them quickly, a subset of them. So if we look at this node 1, and let's say we have a rule that if packets arrive on import 5, so we matched import, then they will be forwarded to 2. So all the cyclic permutations that we can have in this case is 5234 or 5243. So when a packet arrives from 2, then either it can be forwarded to node 3 or it can be forwarded to node 4. But for both of these examples, for both permutations, you can make a scenario that creates one of these loops. So in the first case, so let's say you go to 3, then we look at the scenario B, and we say, okay, in this case, if the packet comes from 5 and then will be forwarded to 2, then from there, it has to go to, on this permutation, it will go from 4 to 5. And then from 2, in this case, it can only go to 4 and essentially end up in this middle blue loop here, and then going back and forth here. In the other scenario, so if you would go to 4, if you have a permutation like that, in this case, it goes from 3 to 5. And then, so here the counterexample is the A. And then since the degree of node 2 is 2, so it can only go back to 3. And then the packet basically ends up in this loop there. So these two permutations are basically not good. But of course, node 1 could also, if a packet arrives on 5, it could also forward it to port 3. So then the remaining permutations would be something like 5342 or 5324. And again, in these scenarios, you can construct an example where it will not detect the path that actually is possible to the destination, but again forward along a loop. So so here, if a packet arrives on port 4, if the packet coming from port 5 go to 3, and then if the packet, if you look at the packet arriving of port 4, according to these permutations, either you can go from 4 to 2, or you can go from 4 to 5, right? And then again, you distinguish the two cases. If it would go from 4 to 2, then you can construct these failures like in the scenario A, and 2 will go to 5, and then from 5, you basically in this case can only go back to 1, and then from 3, again, this is a degree 2 node, so you have to go to 2, and then you come back to 2 to 1, and you end up basically in this loop up here. If you would take the permutation where you go to 5, then the counter example would be C. So here you would end up in the corresponding loop there, and basically you can check these different options you have, and for example, also if you go from 5 to 4, you have these two permutations, but in all of them, you can construct the failures according to one of these 3 scenarios here that will force you to go into a loop. And again, this graph, even before the failures, it's a planar graph, so it will not be possible to have the static rules. And yeah, this link down here, we still need it in this example. That's a technicality. need to explain in detail, but otherwise, here we made sure that all of these neighbors are relevant. So we needed this link to make sure that also 5 is actually relevant. So we need to include it in the permutation. But that's actually technicality. So this is quite a pity because the planar graphs are important class of graphs. And if you look at the Internet Topology Zoo, that's a collection of ISP topologies, router level topologies, or if you look at the rocket fuel topologies, 88% of these graphs are planar, so that's an important class of networks. Data center networks will be very different. They are very dense and very regular. However, ISP networks are relatively sparse. So nevertheless, unfortunately, we cannot hope for too many perfect resilient real graphs that we can install the rules to make them perfectly resilient. However, this was a counterexample for planar graphs, but of course, there are also more special graphs, and we actually checked in this collection of real-world networks that actually almost a third or 32% of the graphs there are belong to the family of cactus graphs. So these are these graphs that they don't have the diamond minor, so there is no faces touching each other. So still quite a number of graphs are like that, and also like roughly half of the graphs are outer planar. So on those graphs, it's actually possible to achieve perfect resilience. And I will not describe the algorithms in full detail. They're actually quite simple. So the idea on outer planar graphs, for example, is that you can use some algorithms known from like classic ad hoc sensor networks that are well studied there from geometric routing, that basically you embed your graph, the outer planar graph, in the plane, so that all the nodes, like how it should be on the outer planar graph, are on the outer face, and then basically apply a right-hand rule to forward just along the outer face of this graph. And so if, of course, if the original graph is outer planar, if you fail links, then the resulting graph is still outer planar, and you try to just basically skip the links that failed along the way, and as long as the graph is connected, you can ensure that you will still find a path that basically brings you to destination. So doing installing rules for this kind of special graphs sometimes is still possible. So this also works, for example, if the graph is just outer planar, if you ignore the source node. So if it's like a clique of 4 nodes, then you can still apply this technique. If it's just after the removal of the source, it's an outer planar graph. So roughly what we know is it's not possible to have a perfect resilience on K5 or the complete bipartite graph K33. We know that if you have a perfect resilience on a graph G, then on any subgraph G prime of G, it's also possible to have perfect resilience. So the idea is simply to take the routing on G and then fail the edges to create the G prime, and then it must still be possible to do the routing on G prime. And interestingly, and a bit more technically, is that if you have a solution for one graph, then you can also get a solution for the contracted graph by doing a simulation argument. So you can basically translate some of the results from a graph G also to a minor graphs of the original graph. So nevertheless, since we have these impossibilities also on K5 and K33, it's of course limited sometimes to which graphs we can still have through that construction to find the perfect resilience table. So we know that it's possible in outer planar graphs. We know that it's possible on every graph is outer planar if you remove the destination or the source. And it's impossible on some planar graphs. It's impossible on every non-planar graph. And and then what we just discussed about the minor. Okay. Any questions so far? Of course, one big disadvantage of these decompositions or Hamilton cycle, especially the Hamilton cycle decomposition to do the resilient routing, but also for the arborescence, is that if you fail over or if you do a bouncing on one of the Hamilton cycles, then the path can be very long to the destination. You may have a lot of hops. So while this is already interesting and challenging to ensure the resilience, of course, in practice, having these long paths is not desirable. And similar, of course, we didn't look into congestion properties. And interestingly, the congestion is again a topic that touches some of the local and distributed problems, but in a new way. And I will also want to quickly show you what's the new perspective that fast rerouting introduces if you look into congestion. And the keyword here is disconnected cooperation, which is one subfield that there are, maybe some of you know, I don't know, some of these papers that also appeared, for example, at PODC. But let's start from the beginning. So if you consider congestion, we can even look at much simpler networks than we did so far. Well, we looked at quite simple ones, but here we can even look at the click. Okay, so a completely connected network with a destination T, and we again need to pre-install local failover rules. And in this case, let's assume just we can match the source and of course the destination. And let's say we have 3 flows in this network. So we have a demand from 1 to T, from 2 to T, and from 3 to T. So we have these 3 flows. And this node T is node 6. And let's say they all want to send this demand to the same node. So how to pre-install the rules for this table? So we can have, for example, at node 1, you could have the following failover table that is say, if it does not work, then if 1 to T is failed, the direct link is failed, then try to go to 2. And if that also failed, try to go to 3. And if that also failed, try to go to 4. And at node 2, you may have a table that says, okay, if, sorry, I need to shift it here once, if that should be 3, 4, and so on. So if this link failed, then try 3, and otherwise try 4, try 5. And from 3, it would also be, if this fails, go to 4, 5, and so on. Okay, so that's the rule. Okay, so that's the rule. So now that's the rule for the red flow. And then from the blue is this is down, then go, as I said, then go to 3, then 4 to 5. So we have, I will explain you later why we constructed exactly like that. The problem if you do the failover tables like that, then if these 3 links would fail, how would the load look like? So for the red flows, the rule will be like this, that we first try to 2. And if this is also broken, we try to go to 3. And then this link is also broken, we go to 4. So eventually at 4, you will actually go to T. And the blue flow will also not be able to go here. So it will also try 3, and then it will also try 4. And the same for the green flow. So the load in this example, if you pre-install the failover rules like this, it will be free on that link to the destination. And of course, you could have solved this problem much better with, let's say, a load of 2. If you, for example, install the rules like that the red will go a different path, for example. So one observation here is that we can represent these failover tables in the scenario where we can match the source this way. We can could represent it as a matrix that is distributed across the nodes, and the matrix always says for this source, what will be the next option to try? So if this is the source and we tried I so far. Then in the matrix, we will try I+1 and then I+2 for the corresponding source, and we could represent for each of the sources such a row that tells the order in which it will try to fail over. So in this case, we could say, okay, if, the first node we will try 1, 2, 3, 4. So this is the example we had before, and then finally from 4 we will be able to go to destination, in this case 6, and then this is the matrix representation of the tables we had before, and then here we would try 2, 3, 4, 5. So and here we would, for node 3 we would try 3, 4, 5, and so on. So in this case, this will be just cyclic orders, and always the same. And by looking at this matrix, you can already see when, and that's the observation, when the load will be high. So the problem is that if the rows of this matrix have similar prefixes, then a single link failure may divert multiple flows because they're always trying similar next node. So the more overlap you have in these prefixes, the more load will accumulate if you have an adversary that just fails the corresponding prefix links. Then other flows will also suffer from that, exactly like it was the case in the example before. So if you do this matrix representation, that is essentially a Latin square. So a Latin square means each node appears exactly once on each row and each column. And this is necessary, otherwise you may have loops in the forwarding, of course. And while Latin squares are good to provide resilience, some Latin squares or some of these permutations will give a high load, and some of the permutations will give a low load. And a bad matrix for the load will be something as we've seen before, where the prefixes are always having similar structure. So in this case, if you would fail the link 1 to the destination, the link 2 destination, 3 to destination, 4 destination, then all these flows will accumulate and give a load of 5 on the last link from the node to the destination. And so all that adversary has to do is fail the first L links to destination. A different Latin square may prevent or overcome that problem. So a good failover matrix may try to use different kinds of entry in these prefixes of the row. So the idea is that so again we want to create. Let me quickly see the time here. Okay, so let me. I think that's fine. I just need I think 3 minutes for this. So if you want to, if you have a matrix like this, where basically the prefixes of these rows are using different elements or unique elements, then it's becoming, you have to fail much more links in order to make the flows go along the same path. So basically the idea here is to make a Latin matrix that the prefixes, if you want to maximize the load on node 4, in this case, in order to maximize the load at 4, you need to fail all the elements on these rows 2, 4, and the more diverse these elements are, the more you need to fail to produce this load. So that's the mechanism here. And this to construct such good failover matrices, this is essentially a known problem or related to the block design, the generating good block designs. And that's kind of the geometric counterpart of the projective plane. So one tool here, or one well-known block design, is the symmetric balanced incomplete block design that has nice properties that we need for these prefixes to be different. And using such a BIBD block design allows us, for example, to install failover rules so that we are optimal up to constant factor in the load. And this this technique or the use of these block designs has been also used for other like very local distributed problems. So they call these local problems problems with disconnected cooperation. So if you don't have the opportunity to communicate at all, then all you can do is basically so there is interesting work by Schwarzman, for example, and Malevich on using such block designs also for other distributed problems that are very decentralized without communication. So that's a similar technique we need here. So the good news here is that there are techniques to solve this, but what is quite intriguing is that we can also show lower bounds that say that if you have link failures, then L link failures, you can basically always fail them in a way that the load will be square root of L even in a click. Although the load could be as low as constant. So for example, you could fail half of all the links. If you are given the failover tables, you can always find a way to fail the links in a way that it's very bad for you as the local algorithm, but there is always a very low load path left. So it's still highly connected. The source and destinations are very highly connected, but then you are forced to basically accumulate the load on a subset of links that is a high price of locality in this case. Okay, so that was a quick excursion on the load. Of course, randomization helps in this case. And if you're interested in these approaches, you of course may ask, how do you randomize forwarding on the router? But we can leave that for the questions. In general, in contrast to wide area networks, data center networks are very dense. So some of these local balancing algorithms from the click, we can still transfer to data center networks that are like fat tree networks or hypercubic networks. So they are coming from the dense side is interesting. Okay, thanks. Are there any questions?
Thanks a lot, Stefan, for. Oh, no, yeah, go ahead. Sorry. Sorry, I interrupted you. If you want to continue, then continue. Otherwise, we ask. Whether...
You mean me? No, no. Please go ahead.
Yeah. No, okay, I personally have one question for. Oh, okay. I personally have one question for earlier parts that for FRR part. There, what you have is that the network is static all the time, yes?
The network is?
Static, like there is no, okay, it's static in the sense that you don't add a new node to add new routes.
Right, right.
And is there a study, like is it at all interesting to study such a thing? In a practical sense, maybe it's interesting, but no, I don't know if it leads to any.
I mean, we are not that far yet, I think, to think about. Of course, networks in practice, they will be evolve and they be extended, right? And new routers may be added to the network. So one interesting question there may be, for example, you are given, maybe you found a perfect resilient configuration or ideal resilient configuration, and now you want to add one part to your network or a router to your network. Can you extend based on the current configurations the configuration to that router in a way that you have to make the minimal changes to the existing configuration or something like dynamic algorithms kind of thing, right? So,
or at least make only local changes, like
right.
up to certain radius, change the configuration, right, but don't change the configuration of the internet.
Right. So that's an interesting question, but I really think it's still we currently still have a lot of problems before looking into that. but it may be a way to, of course, design an algorithm potentially too. I mean, maybe if so maybe you're right, it could actually be interesting, because maybe you can inductively then use this trick you found, but I fear it's difficult. And again, currently we don't even know, for example, whether ideal inference is something possible or not. So then it's, I think, quite early to think how you would extend it. But practically, definitely there. Although I think it's always nice to reconfigure little, but yeah. But in your local area network, if you extend it with one router, maybe it's okay to. Yeah, no, actually, I think it would be nice to, if you could do without too much reconfiguration there. I agree.
Any other questions? You can either unmute and ask yourself or write in chat. Okay. Once again, thanks to Stefan for a very interesting talk and many new topics that you raised, and I wasn't familiar with and enjoyed a lot. Once again, we thank you, and I will leave the scene for introducing Michael by Alexander. Thank you.
Yeah, thanks a lot. So I suggest that we will not make a break between these talks. There will be a longer break at the end of this talk, if that's okay with everybody. Let me just restart the recording.